Hey kids, so in this video we're going to take a look at the content of chapter 16, or at least part of it. So the first concept in chapter 16 is this idea of Bernoulli trials. So we want to look at what makes a situation fit into the category of being Bernoulli trials. So in no particular order, the first thing that needs to happen is that there need to be only two outcomes. And we typically define these two outcomes as a success or failure. Now, keep in mind that success may not be something positive, right? Success just means that's the outcome you're looking for. So it might be, the probability that someone has cancer, and having cancer in that case would be deemed a success, even though it's not something you would want to have. And some notation alert, right? The probability of success, we're going to designate that as a lowercase p. And then the probability of failure, we're going to designate as a lowercase q. And the probability of failure will just be 1 minus p. Because there are only two outcomes, if the probability of success is 0.7, then the probability of failure has to be 0.3 because the two things have to add up to 1 because they are the only two things that can happen. All right, next up, the probability of success has to be constant. So what we're really looking for here is that the trials are either independent or what I'm going to refer to as virtually independent. So trials that are independent are things like rolling a die or tossing a coin and, spinning a spinner, something like that, where if I roll a die and it comes up a 2, the next time I roll it, the probability of it coming up a 2 is still the same. So those trials are actually independent. Now that scenario actually is more unusual when we get into working with Bernoulli trials than the next definition of being virtually independent. So virtually independent comes up when you are drawing a sample without replacement from a finite population. And that's usually what we're doing. So when we get into doing things like confidence intervals and, predicting the population proportion or the population average of something, that's a case where we're sampling from a finite population and we're doing so without replacement. So technically, the trials are not independent. So let's say that, you're looking at left-handed people in the population. I think it's around, I want to say the proportion of left-handed people is around 14% in the whole population. So if I draw people from the whole population without replacement, when I started, taking someone at random, the probability that I get someone left-handed would be 14%. Now, I've taken one person out. So technically, the proportion of people remaining in the population who are left-handed is just under 14% now. But because the population is so large, and I'm drawing out such a small number, for all intents and purposes, that probability is not changing. So that's what I'm talking about for virtually independent. So this is what you're going to cite when we're drawing from a finite population without replacement. And it turns out that there's an easy check for this, and that is that your sample size, which we're going to denote with an n, that your sample size is less than 10% of the entire population. If you want to see a proof of this, you can check out the math box on page 424 in your textbook. It's actually a pretty straightforward proof, so check that out if you're interested. So those are the two things that have to happen. Right? Only two outcomes, which we're going to denote as success and failure, and then the probability of success has to be constant from trial to trial. So let's take a look at an example then. Let's say that M&Ms is going to try this new marketing campaign where they're going to make striped M&Ms. So they're going to make 30% of all their M&Ms striped, and then they're going to mix them up and they're going to package them into bags. So you go out, you buy a big bag of these M&Ms, and you start pulling them out one at a time, and you're looking to find a striped M&M. So we're going to start looking at some questions with regard to this. So our assumption here is that 30% of the M&Ms in that bag are striped ones. Because they've been mixed well, we're going to just assume that that our bag is a representative sample of all of the M&Ms out there, and therefore have 30% striped ones in the bag. So the first question here is, are these Bernoulli trials? Do they fit those two categories? Are there only two outcomes? So when you pull an M&M out of the bag, and we're looking to see whether it's striped or not. So in this case, there are only two outcomes. Even though, there might be 5 different colors in the bag, what we're breaking it down into striped or not striped. So we're taking that outcome that may have multiple outcomes, and we're going to really break it down and make it have only two. So we're going to look at whether it's striped or not. So that first condition is met, right? Either the candy is striped or it's not. And I'm going to go ahead and define what the probability of striped is. So my P is going to be 0.3. And that, remember, P represents the probability of success. And in this case, that is getting a striped M&M. And therefore, the probability that it's not striped is 0.7. So we're going to call that Q. Again, this is just 1 minus P. So we're okay there. There are only two outcomes here. And then we also need to check to see, does the probability of getting a striped M&M stay 30% each time I pull one from the bag? So this is a case where there are a finite number of M&Ms in that bag. We're starting out with 30% of them being striped. And notice back in the question, I did say that it was a large bag. So we're going to have a lot of M&Ms in this bag. So here we're drawing from a finite population, and we're doing so without replacement, right? We're going to take one out, look at it, see if it's striped. If it's not, we're going to pick another one. And we're going to keep doing that until we find a striped one. So here we are going to cite that the number of M&Ms it's going to take will almost certainly be less than 10% of all the M&Ms in that large bag. So we don't have a set sample size here. We don't know how many M&Ms it's going to take until I get a striped one. So here I don't have an N back here on this slide when I talked about the sample size N being less than 10% of the population. That's if you have a fixed sample size, which we're going to talk about those actually our next class session. So for this scenario, we do not have a fixed sample size. But I do know, and I'm pretty confident, that however many M&Ms it takes before I find my first striped one will be less than 10% of all those M&Ms in that large bag. So I'm going to consider this to fit that 10% condition, and therefore satisfy that sort of virtually independent condition, that the probability of getting a striped one is, for all intents and purposes, going to stay the same from trial to trial. So these can be considered Bernoulli trials. So that's that first part. I'm going to tack another check onto this, because when we start doing hypothesis testing, this is something you're always going to have to check. So basically what's happening in this next piece is that we want, in order for this 30% of striped M&Ms to apply to the bag of M&Ms that we have to operate on the assumption that the bag of M&Ms we have is representative of all the M&Ms they make. Because if our bag of M&Ms is not representative of all of the M&Ms, then I can't apply that 30% probability of getting a striped one to the bag I have. So the first two things are what you would check if you just want to check and see if there are Bernoulli trials. But in order to say that P is 0.3, we also need to check that we have a representative sample. So sometimes you'll just check this by saying that the sample was randomly drawn. Here, we're going to assume, because they said that the M&Ms are mixed well before they're placed in the bags, we're going to assume that the bag of M&Ms we have is a representative sample of all of the M&Ms. And again, the reason we need to do that is because if we don't have a representative sample of all M&Ms, then I can't operate on the assumption that 30% of the M&Ms in my bag are striped ones. And I need to assume that, otherwise I'm stuck. All right. So, what's the probability then that the first striped one you find is the fourth one chosen? So here, I'm going to define X to be the number of M&Ms I draw out of the bag before I find the first striped one. So what I want to know here is, I want to know what is the probability that X equals 4. So this is saying what's the probability that the number of M&Ms until finding a striped one is 4. So here, because the order matters, right? If the first striped one I get doesn't happen until the fourth one, that means the first one was not striped, the second one was not striped, the third one was not striped, and then the fourth one was striped. So these are all connected with ands. First one was not striped, and the second one was not striped, and the third one was not striped, and the fourth one was. So that's why I'm multiplying these. And the probabilities are all staying constant because we checked back here that this condition was true. So as long as we have Bernoulli trials, we don't change these probabilities because the trials are independent. So the probability of success, and therefore the probability of failure, is staying constant. So this is the work you would show for a problem like this. So go ahead and define a variable for x. You could also just write it right out inside these parentheses if you want to. But throughout these examples, I'm going to continue to use x to represent the number of M&Ms until we find a striped one. So that works out to be about 0.103. Next example. What's the probability that the first striped one we find is among the first three? So what that means really is, what's the probability that the first striped one is either the first one, or the second one, or the third one? So what we're really looking for is the probability that x is less than or equal to 3. So that's the probability that the first striped one we find is the first one, or that the first striped one we find is the second one, or that the first striped one we find is the third one. So really what we're doing is we're doing this 3 times. And then we're going to add them together because they are connected with ors. So here, that's really just going to be this, right? It's the probability that the first striped one is the first one, plus the probability that the first striped one is the second one, plus the probability that the first striped one is the third one. So the probabilities then are going to look like this. So the probability that the first striped one happens on the first try, well, that's just p. That's our probability of getting a striped one. And then on the second try means we got not a striped one, and then a striped one. So again, these are connected with an and, so I'm going to multiply those. And then here for the third one, I'm going to have not a striped one and not a striped one. So that's going to be 0.7 times 0.7. So I'm just going to write that as 0.7 squared. And then the third one is going to be the striped one, which is 0.3. And that works out to be 0.657. All right, and then the last example we're going to look at is, and it's not really even an example, so we're going to come up with a formula here, and this is on your formula sheet. So now we're looking for an expected value here. We're looking for how many do we expect to have to pull out of the bag until we find a striped one. So here what we're looking for is the expected value of x, otherwise known as the mean of x. So it turns out that that formula, and again, this is on your formula sheet, I'll show you that in a second, is just 1 over the probability of success. And again, if you want to see a proof of that, you can go ahead and check out the math box on the bottom of page 416. So I just want to show you on your formula sheet here this. So here are here's the expected value for that. So you'll notice here that it says if x has a geometric distribution. So a geometric distribution happens, these are ones we use probably the least often of all of these distributions. We're going to talk about binomial distributions in our next class. So a geometric distribution, or a geometric scenario, is where you're waiting for the first success to happen. So for a geometric, you'll notice here that it just says parameter p. So the parameters for something are the information you need in order to be able to use that model. So we're talking about a geometric model, kind of like when we talked about a normal model. The parameters for a normal model are the mean and the standard deviation, right? In order to be able to use a normal model, I have to know where it's centered, so I need its mean, and I need to know how spread out it is, so I need its standard deviation. So it's a similar idea here for a geometric model. The only thing I need to know in order to apply a geometric model is the probability of success. So that's what we're talking about when we talk about the parameters needed. That is the information you need in order to be able to use that model. So here is the mean of that. So that is, again, the expected number of trials until your first success happens. This is the standard deviation for a geometric model. I can say I've never had to use this for anything. So if you had asked me what the standard deviation was for a geometric model, I would have had to look it up. And in fact, I don't even think it was on the formula sheet prior to when they revamped this formula sheet last year. So if you ever do need to use that, it's there, but I've never seen a problem where I've needed it. So the only problems I've seen are where you need to find the expected value, and that's just 1 over p. So again, if you want to see a proof of that, you can go ahead and check out the math box on the bottom of page 416. So that's it for this video. And then, like I said, we'll talk about the binomial model in class in our next session. And that's the one we're going to work predominantly with for a good portion of the rest of the course.